The radiation emitted by the sun spreads out fairly uniformly as a sphere as it travels away from the sun, and by the time it reaches the top of Earth's atmosphere, it's fairly uniform at around 1360 watts per square metre. Now, this incoming solar radiation hits the equatorial regions at a normal angle, so they cop the full amount square on. The polar regions, however, are at an oblique angle to the incoming solar radiation, so the incident radiation tends to be smeared out over a much larger area, which is dependent on the latitude. So the higher the latitude, the less incoming solar radiation. So if you were to look at the latitudinal distribution of the incoming solar radiation at the top of the atmosphere, you'd find that it has a peak at the equator and it drops off to minima at the poles. So that was the incoming radiation from the sun. Now, for Earth to be in somewhat of a thermal equilibrium, this incoming radiation must be balanced by outgoing radiation from Earth back out to space. The outgoing radiation is simply a function of the local temperature. Now, we know that it is relatively warm at the equator and relatively cool at the poles, so the latitudinal distribution of the outgoing radiation is such that it's a maximum at the equator and a minimum as you go towards the poles. This latitudinal distribution is just like the incoming solar radiation. However, if you compare the incoming and outgoing solar radiation distributions, you'll find that there is more incoming than outgoing at the equator, and there's more outgoing than incoming at the poles. This means that there is a net heat gain at the equator and a net heat loss at the poles. Now, if there's a net heat gain in some region, we know that the temperature there will continue to increase. At the same time, if there's a net heat loss in some region, the temperature there should tend to decrease. Now, on the long time scales of Earth, the equatorial regions haven't been continuously increasing their temperature, nor have the polar regions been continuously decreasing their temperature. They're somewhat steady over a long period of time. So there must be some mechanism on Earth that's actually taking excess heat from the equator and transporting it to the polar regions. Now, this mechanism, of course, is our climate. It's Earth's climate, and it's predominantly the heat transport is predominantly performed by the atmosphere and the ocean. So the ocean doesn't cover all of the globe, and depending on where you are on Earth, most of the heat transport is actually achieved by the fast motions of the moist atmosphere as opposed to the relatively slower motions of the ocean. But the heat that is transported by the ocean tends to do so by way of very large scale, basin scale ocean gyres. The oceans don't cover all of the globe, and depending on where you are on Earth, most of the heat transport is achieved by the fast motions of the moist, warm atmosphere as opposed to the relatively slower motions of the ocean. Now, the heat that is transported by the oceans tend to do so by way of very large scale ocean gyres that exist in each of the major global ocean basins. And through the configuration of Earth's continents and the influence of Earth's rotation, the bulk of the ocean heat transport is achieved in these very narrow currents, which are known as western boundary currents. Western boundary currents ride up alongside the continental shelf on the western side of various ocean basins, so that they're on the eastern side of the major continents. Examples of the western boundary currents include the Gulf Stream that goes alongside North America, the Kuroshio that's off Japan, or the East Australian Current from Finding Nemo. Given the fact that western boundary currents perform most of the ocean heat transport, it's no real surprise that they are regions of turbulence and substantial variability, and they exert a major influence on the local weather systems. Now, the poleward water transport of the western boundary currents must be balanced by a return flow. As the warm surface waters reach high latitudes and they release their heat to the atmosphere, they become dense and they sink, and eventually return equatorward as deep and bottom waters in the major ocean basins. While the flow of these deep bottom waters is much slower than the surface waters, their volume is absolutely immense. They can literally fill the ocean's depth. So when you consider the very high heat capacity of water, what this immense volume means is that by changing the temperature of these deep and bottom waters by only a tiny amount, by like 1/100th of a degree, you provide the climate with a mechanism to store vast amounts of excess heat and lock it away from the atmosphere, which is where we live and where we experience excess heat in extreme weather. In this way, the deep oceans can be thought of as a massive heat sink, as somewhat of a thermal regulator for Earth's climate.